Hey everybody and welcome back. If it's your first time here, welcome to this channel. I'm David Townsend. This is the Net Academy where we are learning networks together. And on this video, this is part 8 of the EVPN-VXLAN series. As I always say, that stands for Ethernet Virtual Private Network, Virtual Extensible Local Area Network, two big acronyms, two big protocols in one. What we are going to go through is the data center design considerations and also what is a spine leaf architecture. Why is it different to that of a spine leaf architecture? What protocols do we have running between the leaf and the spines, and maybe between the spines themselves? And overall, how does that then impact the protocols? So in terms of tempo, in terms of the complexity of this part 8, we're actually taking the tone down quite a bit. We've had quite a few heavy episodes, quite a few heavy parts recently over the last few weeks, where we've gone through integrating, routing and bridging, the different EVPN service bundle types, EVPN route type 5 and the data center interconnection, and quite a bit more. So I don't know about you, I'm actually quite excited to take that tempo down a little bit and actually start talking more around the design considerations you have to take into account when it comes to data centers. But also I'm very excited because we are now building up to actually going into the lab and actually start to design and configure these leaf devices, these spine devices, in a spine only deployment and in a separate video, in a separate part, in a spine leaf deployment. So very excited about that, and that's why we always go through the theory first, because we need to understand EVPN-VXLAN, those key terms, the protocols themselves, before we actually go into the lab and configure those leaf spine switches routers and start going through the routing table and seeing and verifying and maybe troubleshooting that network in itself. So as always, I'm not going to talk anymore. Let's actually start off with talking about what do you need to consider from a very high level when it comes to designing a data center. And so I just want to start this part by going through what are some of the things from a networking point of view that you should consider when designing a data center. Now, the things I'm going to go through are obviously not the extensive list. There are huge amounts of areas and protocols and general topics, from air conditioning to power to location of the racks, etc., that you do need to go through when it comes to a data center. But of course, here we're actually just interested in networking itself. And the reason why I want to go through this is because, as we know, data center networks are incredibly complex, incredibly expensive, and as such, they need to be absolutely rock solid, for lack of better words, when it comes to the routing and the networking that they're providing for those servers, those virtual machines. And that's important because at the end of the day, the data center is there to provide connectivity to those servers, to those virtual machines. The network is, as such, just serving those servers, no pun intended there. So it's very, very difficult to go back on a data center network design and deployment once it's done so, once it's been deployed from a traditional config COI perspective. Obviously, there are solutions out there where you can automate all of this, but for now, we're just concentrating on the command line interface. So what is one of the first things that you do need to consider when it comes to a data center? And so the first thing that we need to be aware of when it comes to networking for data center design considerations is actually the number of data centers, i.e. how many data centers are you actually looking to interconnect? Now, you might have some of these on premise or within a campus fabric, or actually over or inside a co-location, so a data center hosted somewhere else. So if we look at it from a routing perspective, what we've obviously got is, say we got DC1 here, just very quickly, and over here we got DC2. Of course, we've got this routing in between, but this is going over a cloud as such. And this will be your wide area network. And there are many different types of protocols, as per my last video, that you can use to connect data center 1 to data center 2. You could do multi-protocol label switching. You could do GRE. You can do over the top or OTT. You can also extend VXLAN tunnels over the WAN connectivity for that DCI, the data center interconnection. And this could be at layer 2 or layer 3. So really the point here is that you do need to take into consider the number of data centers that you do want to connect and how do you want to connect them together. And that really does dictate what protocol you should be using within the WAN itself. As per my last video, this is a huge area, and of course you do need to take this on a per data center basis because every data center is going to be different in terms of the reachability. And that's really the point is when it comes to the number of data centers that you want to connect to together, it's really coming back to this term, and I think it's spelled like this, reachability. So for the reachability, how do you want data center 1 to be connected to data center 2, or maybe even to another data center like data center 3? And what tenants, servers, virtual machines do you want to extend connectivity over that WAN connection? So of course that is a first initial point, and it is a big point. I can't emphasize that enough. Always refer to documentation, what's provided by that service provider, by that WAN connectivity, and also looking inside the data center in terms of what host do you want to have connectivity to other hosts over that DCI and how do you actually want to go around it. But what's the second thing that we need to take into account when it comes to data center considerations for networking? Well, I will say the second thing that we need to look at is actually the underlay itself. Remember, with data center technologies, with EVPN and VXLAN, both of these are essentially overlay technologies. We've got EVPN, which sits on top of the underlay, sits on top of the overlay, and is actually a control signaling protocol that is used by multi-protocol BGP, Border Gateway Protocol. EVPN is a subset, it's a family member of BGP. Essentially, it is IBGP. And when you would start talking about IBGP, they're building peers, relationships, adjacencies to and from these different routers within that same autonomous system. And they're doing so by using their loopback addressing, which means that to have the IBGP connectivity, to provide that EVPN connectivity, you need an underlay. You have to have the underlay, which is where the world of interior gateway protocols actually come into it. And there are many different types of underlay protocols you can use. So my favorite, and I will be honest here, is Open Shortest Path First Routing, OSPF. I think this is a great protocol. It's been around for so many years. It's good, it's solid, it's stable. Software aside from different vendors, of course, there's always going to be bugs out there, etc., etc. But OSPF is just a well-known standardized protocol. But then you've got other protocols like ISIS, or Intermediate System to Intermediate System. Again, very well known, very well adopted in the networks. But you typically see OSPF more in the enterprise network and ISIS more in the service provider network. So would you see ISIS in a data center environment? Maybe. Honestly, I do not know. But for me, it would make more sense to have OSPF as the underlay in a data center world where you can segment that underlay into different areas. And of course, then you've got your proprietary vendor protocol. So if we look at Cisco, they have the Enhanced Interior Gateway Routing Protocol, EIGRP. That's proprietary, it's not standardized, it never will be, no other vendors have really adopted it, etc. But the point is that you need to take into account the underlay routing protocol to come back to this earlier point. How do you want to have reachability for those different tenants, servers, virtual machines, etc. that are connected within that data center? How do you want them to have that routing capability? But another one which a lot of people will forget is EBGP, Exterior Border Gateway Protocol. Yes, you can use EBGP inside a data center for the underlay. I know it sounds strange, but if you look at particular vendors' solutions for data centers, what a lot of them are actually doing is using eBGP as the underlay routing protocol, whereas in historical networking, we've typically seen that from one autonomous system to another autonomous system, so say from an enterprise network to the service provider network. But the reason why you'd want to use eBGP as that underlay routing protocol is because eBGP provides a lot of power, but thus it does give a lot more overhead in terms of complexity. And every spine leaf device would be recognized within a different autonomous system number, or ASN. And thus we can have a lot more power in terms of how you want to change the routing decisions that are made from leaf to spine, from tenant to tenant via leaf to spine. Really, from leaf to spine, we should always be at least 2 hops away to get through that data center environment, even if you're going exterior. But each eBGP allows that additional power that simply OSPF, ISIS, and even EIGRP just simply don't provide, because they're interior gateway routing protocols, whereas this is really an exterior gateway routing protocol, but you can see it inside the data center as an underlay. So just be aware of that. But we do need to take into account what is the routing that would be most suitable for that data center and how you want to use that routing protocol on the underlay to maybe segment parts of the data center or to manipulate traffic routing decisions like we can do in eBGP. The third point is your identifiers. So what kind of identifiers are we actually referring to when it comes to the data center? Well, there's quite a lot. We've got our virtual local area networks, or VLANs, and they are going to be mapped to, on a one-by-one or one-to-one basis, they're going to be mapped to a virtual network identifier. So here we're talking about the local area network, or the virtual local area network, of course. And here we're actually talking about VXLAN, and that is a one-to-one mapping. So typically, if you've got a VLAN of 10, it's recommended to start in the VXLAN world from 5,000 plus due to that 12-bit overhead that you have in the VLAN header. But you could have VLAN 10 mapping to 5,010, just for example, for that virtual network identifier in the VXLAN world. But you also need to think about the other types of identifiers as well, such as the Ethernet segment identifier. So talking more about EVPN. ESI is for multi-homed tenants, multi-homed devices. So we need to identify and define how do you want to identify, no pun intended, more about the puns today, but how you want to identify the Ethernet segment identifier for a multi-homed server, for a multi-homed tenant, and how you want to standardize on that across your data center or across data centers if you want to provide connectivity from one data center to another data center over that DCI over the WAN. But also you need to think about the EVI, the EVPN virtual instance, the numbering. As we know, EVI is basically a concept of all those interfaces and all those leaf-spine devices that are participating in the EVPN domain. So you can have more than one EVI in the same data center because all those leaves on all those interfaces on those leaves and spines are participating in a particular EVPN routing instance. But also if we look at the underlay, so say for example, and again I'm referring to OSPF because I like OSPF as I said, but if we look at OSPF and just draw the line down here, you might want to consider, well, what are the area IDs you actually want to use? Or if it's ISIS, what are the levels, the layers that you want to use and where you actually want to use them? And if we're talking about eBGP as the underlay, guess what? We need to take into account what are the autonomous system numbers that you want to use for each leaf, for each spine device. Now this is obviously quite a lot of information and there's probably going to be more identifiers that you do need to take into account. But typically what you're going to see in the data center world is they're going to take all these VLAN IDs, these VNI IDs, these ESIs, these EVIs, maybe the area IDs or layers - levels for ISIS. And if you're using eBGP as the underlay, the autonomous system numbers, and they're going to block this. They're going to put these into a particular block for particular data center administrative and maintenance purposes. So if you've got DC1 here, you're going to have block 1 for all those VLANs and VNIs, etc. within data center 1. For data center 2, you're going to have a different block for data center 2 for all those VLANs, VNIs, EVIs, ESIs, etc. that within that particular block. And the reason why you want to do this is because it then becomes easier to manage, it becomes easier to troubleshoot, it becomes easier to know based on identifiers which data center, if you've got more than one and providing DCI connectivity, what data center you're actually referring to. So it would make sense to have, say, from VLANs 1 to 100 in DC1, whereas from maybe VLANs 101 to 200 going to data center 2, just for example. And the fourth point I want to talk about is scalability. Now, when we talk about scalability, we are of course referring to the scalability of the data center. So as we know, we've got our spine devices here, and you're going to have your leaf devices here, just below, and these are going to connect to and from each other just like this. And data centers, they scale out, don't they? So as more tenants connect to these leaves, just for example, we can then scale out to provide another leaf for more server connectivities, and then this would connect to those spine devices. And when those spines start to become overloaded in terms of the amount of interfaces they have to provide, then we could just simply add in another spine and connect the leaves to it from there. So, but I'm not just referring to scalability in terms of the data center, you also need to think of it in terms of the protocol itself. So yes, referring back to the underlay, how scalable is that underlay routing protocol going to be? And you need to take this into account from a vendor perspective as well, and a hardware perspective. Every vendor has different hardware, of course, has different switching models for leaves and spines, and they will have different sizes in their routing tables, in their MAC address tables, in their EVPN tables, in terms of the amount of entries that can be stored within that particular device. And of course, what routing protocols they may actually support in the first place. So you need to take into account how can that underlay and overlay routing protocol scale both east to west and north to south. So east to west being across the data center and north to south being going up and down the data center, maybe to an external network. How is that routing protocol going to scale as the physical elements of the data center actually scale out as well? And another point I want to talk about, and you need to take into account, is security. So if I just use this diagram over here, you might have a cloud device here, and this will be your firewall, and through here will be your internet itself. For a data center, you need to provide internet connectivity or some kind of connectivity to the external world, because you need to have that north to south traffic coming in and out of the network, because remote users, ourselves, accessing Facebook or Google, etc., we're essentially accessing information that's stored on a data center server somewhere, and that is going to come through the internet, through the firewall or a security appliance into the data center. So in terms of security, you need to take into account what security appliances are you going to have at the edge of the data center, and the amount of security devices as well. So do you just want to provide traditional layer 4 firewall? I'm not going to recommend that. Or do you want to have some kind of email security appliance, some kind of malware security appliance? Do you want to have maybe some integration with some SASE provider, etc., etc.? There's a lot. Security is a huge topic. Never been my cup of tea, to be honest. But you need to take into account the security of the data center as well, and where those security appliances are actually located, the number of security appliances, what they're going to provide, and even routing to those security appliances. And the last one, number 6, is something called the oversubscription. So the oversubscription ratio. And what I'm actually going to do is I'm just going to clear the board because I need to draw something. And so let me just draw again the oversubscription ratio. Now this, alongside the security, the type of underlay routing protocol, number of data centers, reachability, identifiers, etc. This is equally an important topic, an important area to consider when it comes to a data center design. So if I just draw again our spines here, and I'm just going to draw 3 spines, and here we're going to have 4 leaf devices like so. And they have these servers connected, so I'm just going to draw S for short, and I'm going to do all of these as multi-homed. And obviously every leaf is going to have connectivity to every spine, so let me just draw that quickly. I'm actually getting better with my drawing. I'm actually quite impressed by that. It doesn't look too bad, does it? But here we've got our leaves and here we've got our spines. Now, the oversubscription ratio is quite literally how you want to oversubscribe the bandwidth that's going through the network, and taking into account, will the connectivity between leaf to spine or spine to leaf be able to support that? So if we look at it from the leaf down to the servers here, on each of these devices, so on the leaves, you could have 48 ports, just for example, and all of these could be running at 10 gig. So there, just the calculation is 480 gigabyte of actual traffic, or gigabits per second of actual traffic. But you're going to have 48 ports here as well, so another 480 gig, another 480 gig here, and another 480 gig here. So that's obviously quite a lot of traffic. And between the leaf and spines, it might only be, I say might, it's still very fast, it's still, has a cost element to it, but 100 gig connectivity. But there's a slight difference here where the leaves have 48 ports, but we only then have 3 spines, 1, 2, 3. And there's only a number of uplink interfaces any vendor will support from leaf to spine, for obvious reasons, and depending on hardware, there might be 25 gig or 40 gig or 100 gig or maybe even higher. Depends on vendor, depends on hardware, of course. But there's only a certain number of these uplink interfaces, and every leaf is connecting to each one of these spine devices. So just over the leaf to spine layer here, we have got 300 gig here. We've got another 300 gig here, another 300 gig here, and another 300 gig here. So the ratio, the oversubscription ratio, if we add all these 480 gigs together, is 1,920 gigabits per second of traffic to 300, 600, 900, 1200 supported on the leaf to spine. And this is something you need to take into account, because this is all coming from the leaf devices to the servers, and this is from the leaf to spines and back down again, or to that firewall, wherever it's actually going. But you've got to look at what happens if spine 2 fails, or is going over or through a particular maintenance window, whatever it may be, or maybe the interfaces themselves go down due to some configuration error. The question then becomes, will spine 1 and spine 3 be able to support this amount of traffic? Now, this is obviously the maximum, the theoretical maximum. It's not to say that's the maximum going over this architecture, but you need to take into account what happens if a spine device fails. Will the backbone of the data center between leaf and spine and the additional spines be able to cope with that extra burden and the extra buffering of all those packets that need to be transmitted both east to west and north to south? So yeah, oversubscription ratio, and there's probably a better example out there on good old Google on the internet, but you do need to take into account the oversubscription ratio, and can all of that traffic be still maintained if a particular spine-leaf device does go out of networking for maintenance, or hardware fails, or replacement, whatever it may be. So we've gone through some of the key considerations that you need to take into account when it comes to a data center design. But when we start looking at data center designs, and this is the next part, what is a spine-only deployment, and how does that then compare to a spine-leaf deployment? And that is actually our next part. And here we go. Here is the topology for our spine-only network, our lab. Obviously, it's just an image at the end of the day. But don't worry, we will see this kind of network when we get into the EVPN lab and we start configuring the spines, the leaves, and not so much the servers. But what do we see here? So we've obviously got 2 spines. So we've got spine 1 and we've got spine 2 over here. Leaf 1, leaf 2 and leaf 3. And then we've got these multi-homed servers. Now, I like what I've done here, to be honest, because instead of having multiple servers side by side, now I've only got this one server, and within that, as the reality actually is, within that one server, you could be hosting hundreds, depending on horsepower of that server, you could be housing hundreds of virtual machines, each one in their different VLAN. So you can actually see here, just for this one server here, just keeping it simple, I've got 3 subnets, 3 tenants, one in VLAN 10, one in VLAN 20, and one in VLAN 30, which are then mapped to different virtual network identifiers when it comes to VXLAN. Now, we don't really need to know what the VLAN IDs are and the VNI IDs are. I'm just doing that and going through that just to be a little bit more thorough. But the actual point here is, what is this spine-only deployment and how is it different to a spine leaf deployment? Well, let me ask you a question. As I said on the last part, we have to take into account, you have to consider what is the underlay for that EVPN-VXLAN network, which is running between that leaf and the spine. So if you look at a data center, they would have EVPN running on top of that underlay here, and also then you'd have your VXLAN tunneling going over the top as well. But coming back to my question, what do you think the underlay is for this spine-only deployment? Well, the answer is actually in the title, spine only. It is only on the spine devices where we've actually got that EVPN-VXLAN tunneling. And let me break that down to you a little bit more. You can actually see there's this connection running from spine 1 over to spine 2. You will not find that in a spine leaf topology, or as it's commonly called, a clause 3, or maybe in a clause 5 where you've got a super spine which is then connecting to those spine devices. So you've got a clause 5 or a clause 3, you would have, or you would not have that connection running between the spines, or maybe between those super spines. But obviously we do in this spine only. Why is that? The reason being is because if we look at, again, this section here between the leaf 1 and, or just the leaf devices and up to the spine, all of this is layer 2. There is really no underlay when it's referring to the spine only, because the routing is actually taking place on the spine devices themselves. So from leaf 1 up to spine 1, it's going to be layer 2. From leaf 1 over to spine 2, it's going to be layer 2. From leaf 2 to spine 1 and spine 2, it's going to be layer 2. And guess what? From leaf 3 up to spine 1 and spine 2, it's going to be layer 2 as well. It is quite literally layer 2 everywhere. But as I said, we've actually got these servers with these different VLANs which are associated to these different VNIs on both these different leaf devices, because they're multi-homed, connecting to leaf 1, leaf 2, or leaf 2, leaf 3. So we need a way to get VLAN 10, 20, 30 from both of these servers up from the leaf devices up to the spine devices. How are you going to do that when it's layer 2 everywhere? The answer is trunk. So when it comes to these layer 2 connections, we are going to have a trunk on this link. We're going to have a trunk on this link. We're going to have a trunk on this link. We're going to have a trunk on this link. We're going to have a trunk on this link as well, and a trunk on this link as well. Literally, we are trunking all of those VLANs, or maybe some of those VLANs, again, depending on your reachability. We are trunking those VLANs up from the leaves up to the spines. And additionally, from the leaves perspective, if we look at it from this link here and from these links here and from these links here, it sees that all of these as a link aggregation group, link aggregation group, link aggregation group, or LAG for short. Now on top of that, as we know, or as you might know, you're going to have protocols running such as link aggregation control protocol. In the Cisco world, you've got your own proprietary ones like PAGP, port aggregation group protocol, if I remember correctly. But LAGP is an open standard at the end of the day, hence I'm referring to it here. So we've got link aggregation groups running between the leaves up to the spines. And so we've got layer 2 and trunking everywhere. And by everywhere, I'm only referring to, again, from the leaf devices up to the spines. So really, when it comes to the leaf devices, they are just doing layer 2 bridging. They're quite literally bridging the received traffic, if it's coming up through this connection here, up to leaf 1, they are bridging it from whatever interface it's received on and bridging it over onto whatever interface it needs to go to get to either spine 1 or spine 2. And as I just said, it's on the spine devices where you've got that layer 3 functionality. And again, this is spine only, but where does the concept of EVPN-VXLAN come into it? Well, it's on this link here. It's on the link between spine 1 and spine 2. So whether this be 1 gig or 10 gig, it really doesn't matter. That's just a physical interface speed. What we're building on top of here is the underlay. So the underlay could be eBGP, it could be OSPF, it could be ISIS, it could be whatever. Doesn't matter. We have the underlay routing protocol going between spine 1 and spine 2. And then you're going to have that overlay that goes on top of that underlay. And that will be iBGP because EVPN is basically iBGP. And then on top of iBGP, we're going to have our EVPN signaling and our VXLAN tunneling going across from spine 1 across to spine 2. So let's use an example. Say this server here wants to access a particular application, a particular resource, which is on this server here. So say it's going from VLAN 10, just for example, over to VLAN 20. And as we know, the server can load balance traffic up to leaf 1 or leaf 2 because it's got 2 connections to it. So let's just say it picks leaf 2 as the next destination to send this traffic to. At which point leaf 2 can send it to spine 1 or spine 2, but it's going to pick this layer 2 trunk here and send that traffic up to the layer 3 interface because we're going from VLAN 10 over to VLAN 20. Or from VNI 5010 over to VNI 5020. So we need this layer 3 interface. And it's here when it gets to this layer 3 interface that it's going to go through its MAC VRF and the IRB interface, which is associated to that EVI, and then maybe send that traffic through the VXLAN tunnel over to spine 2. It may do that, it may not, depends what's happening on the network, and then it could come back down to leaf 2 to send onto that server there, or it could obviously come down to leaf 3 and onto the server. Really, the big point here, though, it doesn't really matter if it's spine 1 sends it over to spine 2, is that all the routing is taking place at the spine layer. The leaves are literally just doing layer 2 bridging. And there is one important, well, there's many important parts, but there's one particularly important part that I want to highlight to you. So as we've just gone through, we've got iBGP running between spine 1 and spine 2 as the overlay. And on top of that, you've got EVPN and VXLAN tunneling. Now, in the spine only mode or deployment, you have to be aware about this core isolation feature. Now, in the Juniper world, this is enabled by default. But in a spine-only deployment, you need to enable no core isolation. Let me explain why. With core isolation, in a spine-only model, if the iBGP peering goes down between spine 1 and spine 2, so essentially this goes down between spine 1 and spine 2, what the core isolation does is it's isolating the core devices away from the leaf devices in the event of an iBGP adjacency going down. That is not going to be good. So from the spines facing down to the leaves, these interfaces would then be blocked, essentially. They would not send any traffic down, they would not receive any traffic through. And in which case, the leaf devices here, with all those tenants and servers, etc. connected, they've got no means of communicating east to west or even north to south. That's not good. So essentially all data center traffic could stop. So highly recommend, again, please read documentation, but if you have a spine only model, you need to look at the no core isolation or the equivalent depending on your vendor, and this needs to be configured on those spine devices for this spine only mode. So going through there what spine only is very quickly, and as you can see, really it's just doing EVPN-VXLAN tunneling between spines, IPGP peering between spines, layer 3 on the spines and between spines. Everything else below that is layer 2. It's trunking. So why would you want to deploy a spine only model? Well, again, you've got to think about data center size. For some size data centers, this would be absolutely perfect. Also, you've got to think about this common thing that is money, and here's my sign for the dollars or the euros. I think that is. Apologies if I'm getting it all wrong, but it's money as well. When you have EVPN-VXLAN running on the Leaf devices as well, these devices here have to support the hardware in terms of the additional cam size tables, the MAC size tables, the routing tables, and then you've got the licensing on top of it. Again, I know that's going to vary from vendor to vendor, and that can be a sensitive subject, but it is going to cost more. So depending on the size of the data center environment and where you want that layer 3 functionality, and if you can afford a spine leaf deployment, then maybe actually the spine only model is going to be a nice compromise, especially if you've come from a traditional campus fabric environment. I know that's for the enterprise, where you're used to this traditional tier 3 network, and suddenly you've got this concept of EVPN routing and VXLAN tunneling. So there are compromises, of course, such as the no core isolation, which absolutely you need to be aware of. But how does this then compare to the spine leaf deployment? And silly me, I nearly forgot for this spine only mode, this deployment, to discuss something called the ESI, the Ethernet Segment Identifier. If you've watched my previous videos, you know that this is an Ethernet segment which is being identified via an identifier. So for the servers here, they would have a particular ESI assigned to it for this particular tenant that's behind VLAN 10, and the same for VLAN 20, and the same for VLAN 30. You'd have a different ESI for each one of those tenants, and it's going to be the same over here. But ESIs don't just work from the access leaf down. No, they actually can be configured from the spine layer down to the leaf devices. Why? Well, if we look at it from leaf 1's perspective, it's got a connection from spine 1 down to leaf 1 and from spine 2 down to leaf 1. So you can have ESI running throughout that data center network. And as we know, this is a 10 hex or 10 byte value, which will start with something like 00:11:22:33, etc. Oh, that's a terrible 3, etc., until you get those 10 hexes. Why am I covering this? Well, if you recall a few minutes ago, I did say that from leaf 1's perspective, and this is where I forgot to mention it, it saw that these two connections were a link aggregation group. And from leaf 2, it saw these two connections as a link aggregation group. And from leaf 3, it saw these two connections as a link aggregation group. And then we've got this glorious thing that is the link aggregation control protocol. Ideally, you don't have to run it, but it's advised to run it running over the top of it. But from spine 1, spine 2, does it see these links here going down? And from spine 2, does it see these links going down as a link aggregation group? Or does it see those as an Ethernet segment identifier? The answer is here. It does see this as an ESI. So spine 1 would have a particular ESI going down to leaf 1. And spine 2 would have that same ESI value, whatever it is, going from spine 2 down to leaf 1. And likewise, and let's just say that was ESI 1, just for example. For leaf 2, let's call it ESI 2, just for simplicity, spine 1 would have ESI2 running down to leaf 2, and spine 2 would have ESI2 running down to leaf 2. And it's exactly the same for leaf 3. Obviously, it's going to be the full 10 hex value. The reason why I'm saying this is because, again, with this connection here, with IBGP going over the underlay, i.e. it's the overlay, and EVPN running over the top of it, over this connection from spine 1 to spine 2, we are, well, the protocol is transmitting and receiving those route type 1s, those route type 2s, those route type 3s, the route type 4s, etc., etc., and maybe even the route type 5, depending on where your DCI WAN connectivity actually is, if it's there at all. And this is important because if this link here between spine 1 to leaf 1 goes down for whatever reason, the interface fails, the optics fails, someone disconnects the fiber, the list goes on, spine 1 is going to advertise via that route type 1 over to spine 2 that it's lost the connection to leaf 1 and thus to that server here. And if it wanted to get traffic from leaf 2 up to through spine 1 to leaf 1, it could do so via spine 2. Appreciate the screen's got a bit messy there very quickly, but I just wanted to cover that just very quickly before we go on to, and what we're going to go through now, that is the spine leaf model. And here we go. Here is the spine leaf model. And note there is no connection between the spine 1, spine 2. No, that is absolutely gone. Now, depending on your architecture, you could have layer 3 at the edge, and this would be referred to as edge routing and bridging, or ERB, or you could have the layer 3 all the way at the spine devices, like we did within the spine only model, but this would then be called a centralized routing and bridging model. But before we actually go there, let's actually talk about the underlay itself. Now, with the spine only model, as we have gone through from the leaf to the spines, it was layer 2. But now, when we have this spine leaf architecture between the spines and between the leaves, we actually have layer 3 routing taking place. And now we actually need to take into account and consider the design when it comes to the underlay routing protocol and how you want this to scale, both from a network perspective as the data center scales out, but also from a networking perspective as the routing protocol scales out. Will it be able to accommodate all of the new servers, tenants, virtual machines that are expanding throughout the network? So what you could do is deploy something like OSPF, as I was going through. But then, and coming back to the area IDs, etc., you need to think about, well, where are you going to have the areas? So what you could do is have, and this is just an example, but you could have the spines in area 0, and then maybe each one of the leaves in a different area. So this could be area 1, leaf 2 could be in area 2. Leaf 3 could be in area 3. Or you can completely scrap that idea and just say, no, all the leaf devices are going to be in one big area, and just going with the numbers, I'm going to say area 4. But again, as much as I love OSPF, it is an IGP at the end of the day. And with IGP, it's not as powerful as EGP, referring to EBGP. So let's say we have EBGP running as the underlay here. So with that, let me just finish that P. So here we would have AS1 for spine 1. We would have AS2 for leaf spine 2. We would have AS3 for leaf 1, AS4 for leaf 2, and AS5 for leaf 3. So each one of these devices are in their own autonomous system. This absolutely would work. You could use eBGP as the underlay in a campus fabric network and in a data center network. And the benefit of this is you don't need to worry about area IDs, etc., and the different link state updates and network types, you know, the not so stubby area and the totally not so stubby area, etc., etc., that you get in the OSPF world. Love it, but you know, it is a little bit more complex in that regard. But with OSPF, we can then manipulate the path attributes, the local preference, weight in the Cisco world, AS path, etc., etc. The AS path in the data center should be pretty straightforward because everything is at least 2 hops away to get from source to destination. But we still have, regardless, these path attributes which allow us to do route manipulation. But eBGP, the downside is all that extra overhead you are getting with eBGP. It is complex. It's a lot more of a heavy load on the routing table, and not to mention as well, it's running TCP port 179. So you're going to have a lot more TCP connections running throughout your data center, and you need to ask, is that something you actually do want? All those TCP connections. Again, that is going to be using up X amount of bandwidth, but it's a consideration that you do need to take into account. How about if you use iBGP? Well, iBGP, yes, you could get it to work. I've not tested it, so I do wonder if you'd need a layer below iBGP before you even started referring to it as the underlay. But essentially, it could work. However, the point, whether you've tested it or not, is that when it comes to iBGP, there is this concept of full mesh. So leaf 1 needs to know how to get to leaf 3, and it can only get to leaf 3 via either spine 1 or spine 2, but it will build a connection to spine 1 and over to spine 2, but any routes which come up from the server to leaf 1 and are then advertised onto spine 1 or over to spine 2 do not then automatically get sent down to leaf 3. This is where the next hop self, or NHS, policy comes into. You need to define a policy statement for next hop self, i.e. if this route is being advertised from this spine device, the next hop is myself. So leaf 3 knows where to go to get to that destination. So with iBGP, what you basically need is a full mesh connectivity. So leaf 1 not only needs a connection to spine 1 and spine 2 in terms of adjacency, but it also needs a adjacency over to leaf 3, and leaf 2 needs an adjacency over to leaf 1, and leaf 2 needs an adjacency over to leaf 3, as well as an adjacency up here and down there and across, etc. You can see it gets messy all of a sudden. Or what you could actually do is configure spine 1 and spine 2 to be these route reflectors, where those routes which are coming in from the server to leaf 1 and are advertised up to the route reflector spine 1 are then automatically reflected down onto leaf 2 and to leaf 3. And of course the update would go across to route reflector here. But then you've got to take into account that these would have to be in the same cluster ID. Or would you want them to be in different cluster IDs in the Junos world? And then you get into this very messy world of iBGP and how you want to configure your clusters and your route reflectors. Do you want confederations and all the rules between there? So iBGP can become very complicated very quickly. It's great as the overlay, but in my personal opinion, and I wouldn't want to test it even if it would work, I wouldn't want to use it as the underlay. For me, OSPF just makes sense when using it as a underlay protocol. eBGP, however, I do like the idea of the path attribute manipulation and the routing decisions that you can impact through the path attributes. But coming back to the spine leaf deployment, so as I've said quite extensively there, from the leaves to the spines, everything is layer 3. And let's just say we've got OSPF running here regardless of the area IDs. And so what we now have is all those updates as they come, using the same example from leaf 1, over the overlay, which would be iBGP, EVPN signaling family, and VXLAN tunneling, would automatically be sent on to the spines, spine 1 and spine 2. And those route type messages, because we're talking about EVPN, would be automatically sent down to leaf 2 and to leaf 3. So leaf 2 and leaf 3 learn of all these tenants which are connected to leaf 1 via those EVPN route types. So as you can see, it's basically more friendly, in my opinion, in terms of its deployment. We don't have this connection going from spine 1 to spine 2. We don't have to worry about that core isolation that you get in the spine only model, and you still get all the benefits of EVPN. But now you can additionally choose from an architectural perspective, do you want a centrally routed and bridging model, or do you want an edge routing and bridging model? So obviously there are quite a few more pros to the spine leaf deployment, but again, coming back to it, you've now got more functionality on the leaf devices themselves. They will naturally have to support a little bit more hardware in terms of buffer and memory size, and not to mention the licensing. So the spine leaf might not make sense from a pricing perspective depending on your data center, and of course the size of your data center as well. But regardless, we still have the glorious Ethernet segment identifier, from here, from leaf 2, leaf 3 down to this server here, and from leaf 1 and leaf 3 down to this server here, and even from these links here on the spines themselves could be recognized as individual Ethernet segment identifiers. Literally the full power of EVPN, which is a very powerful signaling protocol, but now we've disaggregated layer 2 to layer 3. Everything from the leaves up is literally running layer 3. And so there we go, everybody. That is the end of this video. That is the end of part 8, which was, as I said, a lighter topic this week because we've gone through quite a lot of advanced topics from IRB and EVPN service bundles, route type 5, and a lot more. So I was glad to take the pace down quite a few notches, quite a few revs, so we can actually concentrate on more of the data center design and some of those key things that you do have to take into consideration when it comes to a data center deployment. But specifically, I was looking at, and we went through the spine only model and the spine leaf model. There are pros and cons to both. The spine only model will be more for the smaller data center in terms of scale, but you need to be aware of that core isolation and the fact that you really only have EVPN and the benefits of VXLAN tunneling between the spines. Everything below the spines, the leaves, etc., is layer 2. We're literally trunking everything from the leaves up to the spines. But when we looked at the spine leaf topology, which is what you see more and more in data centers and a lot more super spines as well, or class 5s, is we then have the ability to define where that layer 3 gateway, that IRB, that layer 3 interface is. Is it on the leaves, the ERB, the edge routing and bridging design, or is it at the core, the spine devices, which would be CRB, centrally routing and bridging? And there are pros and cons to both of those, but it gives you more flexibility, it gives you more choice. But the downside is obviously it is more complex in that kind of deployment and configuration. However, it can also therefore be a bit more expensive when you start looking at the leaf devices. But then you have to ask yourself, well, do you want layer 3 at the leaf layer, or do you want it at the core layer? So again, pros and cons to both of these. But as always, I hope you found that information informative. I hope you found it useful. If you did, please give me a thumbs up. Best way to support my channel. Any questions or comments, let me know down in the comments box. As always, I'm loving the feedback and loving hearing from you all. Other than that, thanks for watching and goodbye.